Welcome back to physics, and today we are going to do a practice problem for you guys on universal gravitation.
Alright, so we have pause the video, write down the question, answer the question to the best of your abilities, then unpause us to watch the answer. Figure out what you did wrong, fix it. So we have a 3.4 times 10 to the 4th kilogram spaceship in orbit, 5.43 times 10 to the 6 meters above the surface of the Earth. What is the gravitational force holding the spaceship in orbit, and what is the magnitude of the spaceship's acceleration towards Earth? The first thing I would do, and probably before you pause us, would be to draw a picture. So we already have a picture of the Earth over here. We should also probably add the spaceship somewhere out here. Now, be careful with this number. This number is from here to here. That is not the radius that you're going to use in your equation. So right now, pause the video, answer the question, then come back and check your answer. Ready, back.
Alright, so hopefully you have an answer to both questions at this point. And Mr. Pierzak is finishing labeling his diagram by adding in some numbers to it. So he's labeling how far above the surface the spaceship is. He should also probably label our radius of our Earth, which is 6.37 times 10 to the 6th meters. And if we want to write down some other pieces of given information, we should note that we have our mass of our spaceship, which is 3.4 times 10 to the 4th kilograms. And since we're also talking about Earth, we probably want the mass of the Earth, which is 5.98 times 10 to the 24th kilograms. If you're confused on where I'm getting those numbers from as far as the radius of the Earth and the mass of the Earth, front of your reference table. Okay, that whole first chart of your reference table is constants. So you have the mass of the Earth, the mass of the Moon, radius of the Earth, radius of the Moon, distance Earth to Moon, distance Earth to Sun. All right there for you. They're common numbers that will come in handy.
Now, please refer back to your reference tables anytime you're confused. There are some really random questions out there, something about like, the force of gravity on some spaceship is this, what is the acceleration? Or find the mass of the sun. Well, all the other information that they don't give you is on the reference tables. So please refer back to that, look at the front page, try to remember what's on there. That way when you're at the test, trying to read through these things, remember what you can get from the reference tables. It will help. What I would like to start with now is writing out the equation for the force of gravity. So we would write out the equation of F sub g is equal to big G times m1 times m2 over r squared. Now, the problem that we have, first of all, what's m1 and m2? Well, m1 and m2 are going to be the mass of the spaceship and the mass of the Earth. So we can kind of redefine that as m sub s and m sub capital E for the Earth. Now we have m sub capital E here, 5.98 times 10 to the 24th. We have m sub s, which is 3.4 times 10 to the 4th. Big G is on your reference table, 6.67 times 10 to the minus 12?
11.
Oh, it's close, minus 11. Also, you should be writing in the units. You don't have to memorize what the units for that number is or are because it's already on the reference tables. But when you write it on your answer for the question, you must write in the units. Now, what do we divide by? Well, we have this number here, which is the distance between the spaceship and the Earth. But remember, this r is really the radius or the distance between the centers. That means the center of the spaceship and the center of the Earth. So this number is not your r down there. You must add the radius of the Earth. So it's 5.43 times 10 to the 6th plus 6.37 times 10 to the 6th. And that's your total radius. Now, if you are going to plug this into your calculator, please use parentheses or do this math first. I would probably just do that math first, then use it to divide into the top. But do what you feel comfortable with. Make sure you use parentheses though. So we do all that math, 6.67 times 10 to the minus 11 times 3.4 times 10 to the 4 times 5.98 times 10 to the 24 divided by that whole radius, and you get a force of...
Almost there. 97,396 newtons.
So that is our force of gravity. Now, you could convert that to scientific notation, but that's totally up to you. I don't really care. You could also round it to 97,000, but that's up to you. I don't really care. All right, good. So we got number 1 done. Check. Number 2. What is the magnitude of the spaceship's acceleration towards the Earth? Now, some of you might be thinking, well, is this spaceship accelerating towards Earth? Of course it is. What this spaceship is really doing is it's actually going around in a circle, so it would be circular motion. Therefore, the acceleration must be pointed towards the center. That acceleration would be the rate at which this spaceship is falling around the Earth. It is not going to be 9.81. It might be close, but it's not going to be 9.81. Remember, if this spaceship was on the surface of the planet somewhere here, its acceleration towards the planet would be 9.81. But it's not here. And the question is, why is it not? Well, the answer is because it's this far off of the planet. So then how do we find its acceleration towards the center of the planet? We have a bunch of different ways to do this. One way would be using a sub c, which is v squared over r. Now, why can we do that? Well, we can do that because we know this acceleration would be a centripetal acceleration. It's pointed towards the center of the planet. But the problem with that is we don't have the velocity. So I wouldn't use that equation. The other equation we have on the reference tables is little g. Little g is equal to Fg over mass. Now, why is this the proper equation? Well, it says on the side of your reference tables that little g is the acceleration due to gravity or the gravitational field strength. At this point above the planet, that would be anything's gravitational field strength at that radius. So then all we really have to do is take the answer we got for number 1, the gravitational force, which is Fg, 97,396, and divide it by the mass of the spaceship, which is 3.4 times 10 to the 4th kilograms.
Now you might be wondering, why did he choose the mass of the spaceship and not the mass of the Earth? And that's something important to consider. When we're trying to calculate this acceleration, we're trying to calculate the acceleration of that spaceship at that point. So since the spaceship is the object at that point, we need to know what is the acceleration on the spaceship, and we have to divide by the mass of the spaceship. So just be careful of that. Since there are 2 masses in here, make sure you know which one we have to use and why.
The other question, well, the other answer to that is why are we calculating the spaceship's acceleration? Well, because the question is, does the Earth accelerate towards the Earth? It doesn't. Something cannot accelerate towards itself. So the only mass we should be using would be the spaceship's mass. Now you get 2.86 newtons per kilogram, which we could also convert to 2.86 meters per second squared, because they are the same unit.
Whichever one you're more comfortable with is totally fine. Since I have newtons and kilograms, I kind of go to newtons per kilogram, but they're the exact same thing.
Now the question, a follow-up question would be, well, if the spaceship was on the surface of the Earth, its acceleration towards the center of the Earth would be 9.81. But here it's only 2.86. Why is it so much lower? The answer to why it's so much lower is because it's so much higher off the surface of the planet. The further away you go, the less weight you will feel, or force of gravity, therefore your acceleration towards the planet would be less. You could go far enough away where that acceleration towards the planet would be technically 0. It would never be 0.0000, but it could be very, 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 very small. And therefore it's technically kind of 0. Meaning that you're so far away from the planet that you don't really feel the force of gravity towards that planet anymore.
So, if you have any questions, please, please, please ask. You do have a test on this and all of circular motion on Wednesday. Okay, we will be here for extra help. We're always here in the morning. We'll be here after school tomorrow on Tuesday. If you have some questions, please ask. and make sure that you are getting comfortable with it. Make sure, even if you didn't get to that correct final answer when you did it on your own, that now you go back, plug those numbers in on your calculator. You need to practice plugging them in. It sounds silly, but make sure that you can plug in with the scientific notation and get to the same answer that we got to.
And before we actually stop this video, I have one more question for you. I just thinking of, would this change, would the question or your process change if we had written, what is the centripetal force? What is the centripetal force of the spaceship at that point? Would your process change? And actually fill that in the Ed puzzle. And that's it. Have a great night.